Another approach for determining the nature of a stationary point is to use the second derivative test. So if I have a function y is equal to f of x, the first derivative is dy dx. And I guess dy dx is equal to some function like, well, I'll call that g of x. If you take the derivative of this function as well, so the second derivative, which is d2y dx2, you get another function. So that's what this d2y dx2 means. It means if you have a function, you find the first derivative and then you find the second derivative. So you differentiate twice, and I'll show you examples shortly. So here's how the second derivative test works. If the second derivative of a function is positive at the stationary point, so by x star I mean the x coordinate of the stationary point. If the second derivative is greater than 0, that means it has a positive value. Numbers greater than 0 are +1, +2, +3, so positive numbers. If the second derivative is greater than 0 at the stationary point, the stationary point is a minimum. If the second derivative is less than 0, so if the second derivative takes negative values or has a negative value at the stationary point, then the stationary point is a maximum. If you find that your second derivative is equal to 0 at the stationary point, then the test is inconclusive. So that means you don't know whether the stationary point is a minimum or a maximum. So you have to use a sign test in such a case. So imagine you have a function like y is equal to 3x squared. If you wanted to find the first derivative, dy dx, you just differentiate this right hand side and you get 2 times 3, which is 6, times x to the power of 2 minus 1, which is 1. So dy dx is equal to 6x in this case. To find the second derivative, you have to differentiate again. And the symbol for the second derivative is d2y dx2, which is equal to, well, when you differentiate this, well, okay, I'll leave the 1 there. It's 1 times 6 times x to the power of 1 minus 1, which is 6 times x to the 0, which is 6. So obtaining the second derivative is just a case of differentiating twice. You already know how to differentiate. That means you can easily adapt that to determine the second derivative of a function. So earlier in the video, the sign test was applied to this function, and we determined that the stationary point of this function is a minimum. When we sketched the tangents, we had something that looked like this, so we knew that we had a curve of this nature. So we have this function has a minimum as a stationary point. We used the sign test to determine that, and that took us a couple of steps. The second derivative test is a faster approach in this case anyway, because all you have to do is first determine the first derivative, dy dx. So differentiating gives 2 times, well, first term, 2 times 3 over 2, which is 3, times x to the power of 2 minus 1, which is 1, minus the derivative of 6x, which is 6. Then you have to differentiate again to determine the second derivative. In this case, that is 1 times 3, which is 3 times x to the power 1 minus 0, and 1 minus 1, which is 0, minus the derivative of 6, which is 0. So the second derivative in this case is 3 times x to the 0, which is 3. So in this case, you can see that d2y dx2 is equal to 3, which means it's a positive number. It has a positive value, which means it's greater than 0. And the technique actually is to determine the value of this second derivative at the stationary point. Because d2y dx2 is a constant 3, it means that we don't even have to bother checking what its value is at the stationary point, because we already know it's equal to 3. It's a constant. It's the same everywhere. So in this case, d2y dx2 is greater than 0. Check out the rule. It says that when d2y dx2 is greater than 0, what you have is a minimum at the stationary point. So we have a minimum, and that agrees with the result obtained by using the sign test technique. So it's a minimum because d2y dx2 is greater than 0. This was, well, we determined this in essentially 2 steps or 3 steps, depending on how you want to count it. Much faster than the sign test approach. We'll try another example. Here's another quadratic function. This was visited earlier, and using the sign test, we determined that this function has a maximum as the stationary point. So we had something like this when we sketched the tangents, so we knew that the curve looked something like, well, something like this, which has a maximum. Let's apply the second derivative test. So find dy dx. dy dx is equal to minus 8x plus 0, so minus 8x. And the 2y dx2 is equal to, when you differentiate this expression, minus 8. So the 2y dx2 is less than 0. And you know that when the second derivative is less than 0, the stationary point of the function is a maximum, which agrees with what we obtained from the sign test, but we were able to determine this in fewer steps, in less time, much less time. So we have a maximum. So what this means is the stationary point of this function is a maximum. So I'll just summarize the technique. You have a function that you want to determine the nature of its stationary point. What you have to do is determine the second derivative. So you differentiate, then you differentiate again. If the second derivative is less than 0, the stationary point of that function is a maximum. If the second derivative of the function is greater than 0, then the stationary point is a minimum. If you get that your second derivative is equal to 0, then it's inconclusive, and you have to use the sign test to determine the nature of the stationary point. So far, we've applied the second derivative test to determine the nature of the stationary point of two functions. In the first case, we determined that the 2y, well, the second derivative, the 2y dx2, we determined that it was equal to 3, which is a positive value, so it's greater than 0, so we determined that the nature of that stationary point was a minimum. In the second case, we determined that the 2y dx2 was equal to minus 8, which is a negative value, so less than 0, so the stationary point in that case was a maximum. But we haven't focused on finding the value of the second derivative at the stationary point, because that's what this means. This x asterisk refers to the x coordinate of the stationary point. We haven't stressed this, and we haven't treated it with enough respect, and we need to. So I'll give you an example that allows us to. So let's focus on this example. So this is a function y is equal to 2x cubed minus 12x. In order to determine the nature of the stationary point of this function, you need to determine the sign of the second derivative. So let's find the first derivative, dy dx. Differentiating this right hand side gives 6x squared minus 12. Differentiating again to obtain the second derivative gives 12x minus 0, so 12x. What's the sign of the second derivative? Well, the second derivative is 12x. What's the sign? We don't know. It varies, because if x is minus 1, the second derivative becomes 12 times minus 1, which is minus 12. That has a negative value. When x is 1, the second derivative becomes 12 times 1, which is 12, which is plus 12, which has a positive value. So at this point, you can see that this x value becomes important in determining the sign of the second derivative. The rule says you need to find the value of the second derivative, the sign of the second derivative, at the stationary point. So we need the x coordinate of the stationary point in order to determine the sign of the second derivative, the important sign anyway. You know that at the stationary point of any function, dy dx is equal to 0. So for this function here, y equals 2x cubed minus 12x, dy dx, when dy dx is 0, so this is dy dx, 0 is equal to 6x squared minus 12, which means that 6x squared is equal to 12, x squared is equal to 2, so x is equal to plus or minus the square root of 2. So x is equal to plus root 2 or minus root 2. So this particular function has two stationary points. At one of the stationary points, the x coordinate is plus root 2. At the second stationary point, the x coordinate is minus root 2. So let's focus on the first stationary point, where x has a value of plus root 2. The value of the second derivative at this stationary point, dy dx2, at x is equal to plus root 2 is equal to 12 times the x coordinate, which is 12 times plus root 2. So I'll just write root 2, and that's 12 root 2, which has a positive value. So at this stationary point, or let's put it this way, the second derivative when x is equal to root 2 is positive, has a positive value, it's greater than 0. So at this stationary point lies a minimum. So the nature of that stationary point is as such, it's a minimum. At the other stationary point, when x is minus root 2, I'll just do that down here. So at the other stationary point, when x is equal to minus root 2, the second derivative, the 2y, the x2, so the 2y, the x2, when x is equal to minus root 2, is equal to 12 times x. In this case, x is minus root 2, so 12 times minus root 2, which is equal to minus 12 root 2, which is a negative number. So at this second stationary point, the 2y, the x2, so the 2y, the x2, when x is equal to minus root 2, has a negative value, so it's less than 0. So what you have there is a maximum, according to the rule. A maximum. A maximum. So the graph will look something like, I'll just sketch the graph. So this is the x, or axis, y-axis. There's a stationary point when x is minus root 2, so let's assume that's somewhere here. So minus root 2. There's a stationary point also when x is root 2. At this stationary point we have a maximum, so it's going to look something like this, a maximum there. And at the other stationary point when x is minus root 2, what we have is a minimum. So you can see that for this first, well, this stationary point, which is a maximum, the x coordinate is minus root 2, and for this other stationary point, which is a minimum, the x coordinate is root 2. So the function I gave originally will have a sketch that looks something like this. The key thing now is that for that function there are two stationary points, as you can see here, a maximum and a minimum. And the key thing I've stressed is we found the sign of the second derivative at the stationary points, and we did that by substituting the x coordinate of each of the stationary points. This function had two stationary points, so for the first one, which has a positive x value, we substitute that positive x value and we obtain a second derivative that is positive, is greater than 0. Positive second derivative value, so it's greater than 0, so we have a minimum at this point. For this point here, the x coordinate is negative, replacing x with this value. So this is the x coordinate of the other stationary points. Replacing x with that value gave a negative second derivative value. So the second derivative at the other stationary point is less than 0, which means that a maximum lies at that stationary point. So that's the second derivative test.